unit 1 and 2 transformations. Let's go y. This is the basic form that you're gonna find all of your graphing equations in, all of them. And as you know, A is your vertical stretch, B is your horizontal stretch, well, divided by B. We'll get to that. H is your horizontal shift, left and right. K is your vertical shift, up and down. Okay. And if A is negative, that means it's a vertical flip. If B is negative, it's a horizontal flip. Okay. So basic stuff. You all probably know that. But just as a reminder, and so let's say we have this graph over here, y equals 2x. If I want to transform that, let's say make it minus 2 plus 2. Okay, how would I do that? Well, first, the thing I added is my h value and k value. This was already there, just don't worry about it. This, let's say this is our function 2x. Because that's what f means. F just means it's something happening to x. It could be root, absolute value, it could be squared. That's what this f is for. It's like a general form that all of your equations can be in. Okay, so to do this, all this is saying is, remember, h value is flipped, so the sign is flipped, so h value is 2, k is 2. All this is saying is it's moved 2 to the right and 2 up. So that's your new equation, or well, new graph. And yeah, that's your basic summary on that. The main thing about any type of graphing, okay, the thing that's going to help you the most, mapping notation, because you can use this in any of your graphing units, any of them, and it works for any transformation graph. What it is your x value divided by your b plus your h, because remember, if you go back, the b and the h value, they're inside the function. Okay, so they affect your x value. The a and the k, they're outside of the function, so they affect your y value. So your mapping notation is x divided by b. Remember, b is always like a flipped stretch, and that's why we divide. And then your a value times your y value plus your k value. So in this graph, our a value is 2. How about let's make it, yeah, no, never mind, never mind. Your b value is 1, 2, it's always the same. H value is, flip the sign, -1, and k value is also -1. So what you do, you just take some key points, okay? So these are our 5 key points for this graph. Since it's not an obvious function, okay, we'll get to the obvious functions later. It's not an obvious function, so you can't really predict how it's going to look, so you have to do all the points. But for example, let's say a parabola or something, you know it's going to look like that, so you can just take like 3 points and transform them like here, and you know it's going to look like that, so you just use those 3 points and that's it. But as I said, mapping notation works for anything. So what's our first one? Let's take this point for example. It's -6 and 3. To transform this, your new point for your new graph is going to look like -6 x value divided by b, which is 2, plus your h, which is -1, okay, comma, your a value, which is 2, multiplied by your y, plus your k, which is 1. Okay, so your new value becomes -6 divided by 2 is -3, and -3 minus 1 is -4. Okay, and 2 times 3 is 6. 6 minus 1 is 5. So that's it. Your new point becomes minus 4 and 5. Where is that? Minus 4 and 5. That's one of your new points. Now you do that again for all these other points. And then you're going to have a graph that looks like this. And that's it. You don't have to look at the graph and be like, oh, it's a stretch of 2, so I stretch it like that and do this, because that's going to cause most of the mistakes. You just take mapping notation, you plug all the numbers in, find all the numbers, you plug all them in, and you don't even have to worry about the reflections. Okay? Like if it's a negative a value, that's it. You just take it as a negative a value, you plug it in as a negative a value, it does the flip for yourself. Okay, so for any equation, what do you do? The first thing you do is you draw the parent function, or just have the picture of it in your mind if you can do it, like that. Draw the parent function, and then you apply the transformations. My suggestion, mapping notation all the way. Any question, just mapping notation. But with questions like these where there's no stretch or anything weird, the only thing that's happening is h and k values. It's easy to do it just looking at the by just looking at the graph too. So you apply the reflection first, okay? Because it's a negative a value, right? Negative a value. That means it flips vertically. It flips over the x-axis, flips vertically. And the other thing is it shifted to the right one because the h value is 1. Remember, change the sign. And then 5 down because the k value is negative 5. So that's going to be your new function. And then same with radicals. You draw the parent function, y equals root x. Okay. So the points that stay the same, the key points, 0, 0. Oh, well, not stays the same. It's just the points that are pretty easy to find. 0, 0, 1, 1, 4, 2, and then sometimes you can get away with a 9, 3. And so same thing here. Wherever you can, just mapping notation all the way. You know what? Let's do this one with mapping notation. A is 2, B is nothing, so 1 is being multiplied. H is negative 2, let's change the sign. K is 2. Okay, and mapping notation, x over b plus h, ay plus k. First point 0, 0 becomes 0 over b, 0 over 1 plus negative 2, and ay plus k. So 2 times 0 plus 2. So 0 over 1 is 0, minus 2 is minus 2. 2 times 0 is 0, plus 2 is plus 2. So our first points is gonna be here. Our second point, 1, 1. I'm just gonna do it in my head, but you can try it on a piece of paper too. 1 divided by 1 is 1, minus 2 is negative 1. And then 2 times 1 is 2, plus 2 is 4. So that's my second point, negative 1 and 4. And since you always need 3 key points, okay? Any graph, 3 key points. Let's just do one more. 4, 2. That turns into 4 divided by 1 minus 2, so 2. And 2 times 2 is 4 plus 2 is 6. So it turns into 2, 6. Did I do that right? 4 minus 2, and then 4 plus 6. Yeah. So those are my points, and I'll just make the graph like that. Yeah, that's it. So whenever you can, mapping notation. Okay, moving on. When you're graphing radicals, okay? When you're graphing radicals and it's not linear, it's not like one of these ones, because this one, the x power 0, there's no absolute value or anything. Whenever you see like an absolute value or an x square, then it's a bit different what you do. But all you do, you just graph your parent function and you use the graph itself to graph the next one. So, wait, why is this shifted? Uh, okay. That's weird. Okay, but as I was saying, you just have the parent function, and then you just all you do is you just square root the y values. So 0 0, your these points stay the same because the square root of 0 0, square root of 1 is 1. Then you find the next good one, which is 4. Square root of 4 is 2. It comes here. Square root of 4 is 2. It comes here. Okay, and then you can find more points, but as you know, 3 is all you need. So, and you know what a radical graph looks like. So you just graph it like that. And the one thing that radicals cannot be, they cannot be negative. Okay. So what you do, you just ignore the negative values altogether. And after graphing the parent function, this one 0 0 stays the same. When the y value is 1, that stays the same. Next good value is 4. So that's here. So I'm gonna square root that, and it's gonna come down here. This one 4 is here. I'm gonna go, and then you just connect them, and you know it's gonna look like that. So you just draw that. It's this one is not a good. I'm sorry, it's not a good one, but it is just gonna look like that. So with non-linear radicals, okay, it's almost the same thing. You just graph the parent function, but instead of using transformations like this, you just use the graph itself and find the points. Okay. Next up, inverses. With inverses, all you do is you flip the y and the x. So if f of x is 3x plus 5 equals 4, like y is 3x plus 5 over 4, then f inverse of x would be x equals 3y plus 5 over 4. And now we solve for y. So, what do you call it? This multiply both sides by 4, subtract the 5, becomes 4x minus 5 equals 3y. Divide both sides by 3, and you get y equals 4x minus 5 over 3. And that's f inverse of x. Keep in mind, f inverse is not the same as 1 over f of x, okay? Exponent laws don't imply to f inverse. This is just the notation of inverses. One more thing, if you this we just learned this in composite functions. If you take the inverse, if you do the function of an inverse, because all the numbers cancel each other out, all you should be left with is x. So let's try that. So f of f inverse of x, this becomes f of 4x minus 5 over 3, because this was our f inverse, right? We just plug that in. And if you plug this in instead of the x here, you get 3 4x minus 5 over 3 plus 5 over 4. Now these three cancel. When these three cancel, you're left with 4x minus 5 plus 5 over 4. The negative 5 and 5 cancel. And then the 4 and 4 cancel. You're just left with x. And that's how you know that they are inverses of each other. So that's the algebra of inverses. If you're looking at it graphically, the same thing applies. What's this point? Negative 6 and 4. All you do is you flip the x and your y. So it becomes 4 and negative 6. So your new point is 4 and negative 6. Same for all the other key points. So this is negative 2 and 3. It becomes 3 and negative 2. This is 2 and negative 2. It becomes negative 2 and 2. This is 3 and negative 2. It becomes uh, 3 and negative 2. It becomes negative 2 and 3. And then this point is 6 and 4. So it becomes 4 and 6. So your graph looks like, wait, 3, negative 2, 3, 3, negative 6, 3. Oh, it's negative 6, 3. Sorry, it's here. So your graph looks like this. Your new graph looks like this. It looks weird, but all it is, it's like a mirror image over this line, y equals x. So another thing about inverses, they're mirror image, they're reflections of each other over the line y equals x. Okay, now it's time for one-to-one functions. I'll take a little more time on this because we did it way before. So just bear with me. What is a function? So a function is when you put in an input and you only get one output. So this is not a function because let's say for the input 4, my answer is 3, but it's also like 6.9 or 6.8, 6.7. So this is not a function. Remember what we used to do to figure out if something was a function or not? We did the vertical line test. If at any point on a vertical line there's two different points of intersections, that means there's two outputs for a single input, then it is not a function. So examples of function: this is a function, okay, this is a function. As long as one input only has one output, it's a function. Now for most functions, let's say this parabola, if you take the inverse of it, your result will not be a function because inverses are almost like 90-degree flips. Okay, and if you flip it, where's the where is the flip button? Whoa. Turn into a circle. uh like this turned 90 degrees, right? That's its inverse. So if I do, okay, stop. If I do a vertical line test now, it doesn't work, right? What if I want to know that if my inverse will be a function before? Well, now that vertical line test that I was gonna do, it turns into a horizontal line test, okay? So that's it. To check if the inverse of a function is gonna be a function, you have to do a horizontal line test. So now it doesn't follow a horizontal line test, so it's not gonna be a 1 to, this is not a 1 to 1 function. Okay, one-to-one function is when the normal function and the inverse is they're both functions. But what we can do is we can add a restriction to this function so that what do you call it? It becomes a function when we turn it around, when we inverse it. Okay. So for let's just say y equals x squared. Okay, this is it's just a sketch. Bear with me. But y equals x squared, right? When we inverse it, okay, when we inverse it, it becomes x equals y squared, and to isolate y, it becomes y equals root x. Okay, but you remember our radical, what our radical graph looked like? It looked like this. Okay, it had the restriction x had to be greater than 0. But technically, if you graphically inverse it, it should have been like this, right? So that's the thing that we do. We add a restriction to it. That's usually a hint is that's to do with the vertex. So whatever your x value of the vertex is, x has to be either greater than that or less than that, and then it's going to be a function. So let me give you another example of that. Okay. So if my thing is this, okay, uh, all I need to do is find my axis of symmetry, which is -3. Okay, and I just do x has to be greater than -3 or x has to be less than -3. Because when I inverse it, right? When I inverse it, this 3 0 -3 0 is gonna look like this. Okay, this. But if I have one of these restriction, it's gonna be only one of the lines. Okay, only one of the lines because I have this restriction. And so it passes the vertical line tests. So a recap, one-to-one functions is when the normal function and its inverse are both functions. They to find it, you have to do the horizontal line test on the original one. If it fails the horizontal line test, it's not a function, but we can add a restriction to it. And I'm pretty sure in the curriculum it's only the parabolas, like quadratics. So you find the axis of symmetry and you put the restriction on it based on that, and then it only has one leg. It passes all the vertical line tests, so we can turn it into a one-to-one function by adding a restriction. Okay, so yeah, that's one-to-one functions. And then the last thing we need to go over, probably the easiest of them all, is solving radical equations. The first way you can do it is by graphing, which is pretty easy. You just take the left side, you graph it, so this line. Then you take the right side and you graph it, so this line. And wherever they intersect, your answer is going to be that x value. So your answer is x equals 4. That's it. Now, if you were to solve it algebraically, first what you would do is you would isolate the radical. So we would subtract 1 from both sides. You get root x plus 5 equals x minus 1. Okay? And then you would square both sides to get rid of the radical. You get x plus 5 equals x squared minus 2x plus 1. Okay? And then now it's just a normal quadratic. So minus x minus 5 minus x minus 5. 0 equals x squared minus 3x minus 4. 0 equals x plus minus 4 x plus 1. And so your x is either 4 or negative 1. But with radicals, you have restrictions. Your radical, remember, cannot be negative. So whatever's inside your radical has to be greater than equal to 0. What's inside your radical? X plus 5. So that means x has to be greater than or equal to negative 5. And now you see that both of these pass that restriction, but you still have to check for extraneous solutions. Okay. Or wait. No. But what happens? But what happens with radicals or anything that could have a potential restriction, right? Sometimes you get extraneous solutions, so you always have to check. So if I check x equals 4, I get 4 plus 1 plus 1 equals, I mean 4 plus 5 equals 4. So root of 9, which is 3, plus 1 equals 4. 4 equals 4. That's correct. If you check negative 1, you get negative 1 plus 5 plus 1 equals 1. And this is 4. Root of 4 is 2. And you get 3 equals 1, but 3 does not equal 1. So this is not a solution. So your only solution is x equals 4. So always check for extraneous roots. Okay, to summarize, this is the general form for all your transformations. Okay, A is your vertical stretch, B is your horizontal, the flipped version of your horizontal stretch, H is your left and right move shift, horizontal shift, but the sign is always flipped. K is your up and down vertical shift. Okay, this is the most important thing in all of grade 12 pre-cal, mapping notation. Just fit this into your head. Anytime there's a graph, you take the parent function, you take the original graph, you plug the points in, you plug all the A, B, C, D, A, B, H, K values in, you get the new points, you graph those points. That simple. You don't have to worry about, oh, is this reflection, is this stretch. Just plug everything in and it works. Next up, the restrictions. Radicals can't be negative. And also remember to check your answers when solving algebraically. And graph of radicals, if it's linear, is just normal ABHK values like this. But if it's not linear, you just graph the parent and use the graph to graph the new graph, to graph the actual radical graph. And then coming to inverses, it's just flipping y and x. And the property, a property of inverses is if you do the function of the inverse, you should end up with just x because all the other stuff cancels out. And then one-to-one functions. If you need to go back to that, please do. Don't be confused, and you can ask me for questions if you want. One-to-one functions, your original function must pass the horizontal line test, because if your original passes the horizontal line test, your inverse is gonna pass the vertical line test and it will be a function. And if it's not a function, in some cases, quadratics, you can add a restriction to make the inverse a function. Okay? And that's it for today. Thank you.